Okay, last week we discussed some of the basics of noise in analog communications, right? So remember that what is ST and WT? We also discussed NT. Remember? The ST is what is transmitted from the transmitter. Let's briefly draw the diagram. So here's a transmitter. At the end of the transmitter, let's say we have an antenna. Through the antenna, we are transmitting some signal. That is ST, right? ST is transmitted over the air or over the channel, and eventually we have a receiver. Let's make receiver a little bit big, like this. This is a receiver. In between, in the channel, we have noise, right? And the noise that we are looking at is additive noise. Additive noise, right? And we write that the additive noise as a WT. That means the noise is added into the transmitted signal. So what is received right here is ST plus WT. That's what you receive, right? At the antenna. That's what you see here. This RT is right here. Okay, so we are receiving transmitted plus WT. And one thing that you want to remember is what is this WT and what is the characteristic or what is the frequency response of this WT. That's something that we want to remember. This is not just any noise. Okay, this is a very special noise. Why is it special? This is white noise. White. And also Gaussian. That's why this is special. We call that as a AWGN. So the reason that this is a special noise is because this is a white noise and this is a Gaussian. That's why this is special noise. So what we want to remember is what this white Gaussian basically means. Okay? White basically means is that if you look at this WT, noise in the air, from the frequency domain, okay, I'm basically looking at this noise. Okay, when you look at this noise from the frequency domain, this noise has equal power for all of the frequencies. That means this is white. What is the opposite of white noise? There's another noise called the colored noise. Colored noise, meaning that the noise has some color. It doesn't matter white color, blue color, whatever color. So what we differentiate is either white noise or colored noise. So just to compare, if you look at this colored noise in frequency domain, what would it look like? It's not going to be flat. If in the frequency domain, if the power spectral density shows the flat response, that means white. Colored noise is something like this, not flat. Okay, something else. So if you have some high power, large power into a certain frequency, and some other frequency is a little bit smaller power, that means this one has a certain color. Think about it, right? When you look at the RGB, you know the RGB has a different frequency, right? Red color has a certain frequency, green, blue, each one has a different frequency. And now think about that the blue has a little bit higher power than red and green. That means it's like the white, it's not white. It's going to be a little bit bluish color, right? So therefore, white color means the equal power for all the frequencies. Colored noise means some other, not equal, some other power spectral density, right? So we only have two different type of noise. We are not looking at colored noise because this is pretty complex. It's very complex. So forget the colored noise. I just introduced because to compare. Okay, just to compare. Forget the color. What we always see is white color, white noise. You know Gaussian, right? When you look at the this is a frequency response of the noise. But when you look at the time response, the noise is always like up and down, up and down. Each one has a certain amplitude, right? Amplitude. So if you look at this amplitude variation, that follows a Gaussian. That's our noise. So this is our frequency response in the air, right here, right? However, what we always look at is eventually in the receiver, we want to recover the original message. Here is the original message. Original message here, right? You always have original message, MT. And our goal is eventually we want to recover the original message back. So in the receiver, you need to do something. And first thing to do in the receiver is band pass filter. And after that, you do demodulation and something like that, right? Some other processing here. First thing at the receiver is a band pass filter. Right here, after band pass filter, what do you get? You're going to get this. That is XT. Right here, XT. So what is XT? XT is ST, same ST, plus different noise. It's actually same noise, but it's this MT, when you look at, this is WT, so it's a WF. No, it's this picture is PSD, power spectral density of WT. Right here is power spectral density of NT. And this power spectral density of NT look like this. It's a flat, but because of the band pass filter, these frequencies will be rejected. Right? Why? Because of band pass filter. This RT goes into the band pass filter. Of course, band pass filter has its own bandwidth, right? This is band pass filter. And RT is ST plus WT, but WT has a flat for all the frequencies. But think about this is an input to the band pass filter, right? But band pass filter has a bandwidth. So what's going to be the output? The output will be like this, right? Because the band pass filter will pass only this frequency, all the other frequencies will be rejected, right? All the other frequencies will be blocked. So these frequencies will be blocked. I'm looking at only the noise part. So this is a noise input to the band pass filter. This is the output of the band pass filter, right? So this is a noise, NT. That's a power spectral density. What about ST? ST, this is our signal, our message modulated by some analog modulation. Maybe it's AM, FM, doesn't matter, right? After modulation, this message will be eventually converted to ST. So this is what we transmit over the air. ST, in time domain, maybe it looks like something like this, right? And in frequency domain, of course, it has its own bandwidth. But this ST frequency response, this frequency response bandwidth will be inside this band pass filter, right? Otherwise, you will be rejected. Your signal will be rejected. So that should not happen. So ST frequency response will be inside this band pass filter. So ST will just pass band pass filter. Will be just bypass. So therefore, ST right here, we still have ST at the output. ST is unaffected by band pass filter. Only the noise will be changed to NT, like this. That's the story. So now you see the difference between RT here and XT, right? These two are different, like this, right? This is RT here, and XT is right here. Eventually, what we are learning right now is the demodulation and modulation. Modulation is done here. Demodulation is here, right? So from the demodulation perspective, from the demodulation point of view, what is important is XT. because xt is going to be the input to the demodulation, right? That's what matters from the demodulation point of view. And inside the demodulation also, what we always calculate is SNR. We're going to calculate the SNR. Okay? We're going to calculate the SNR. So how do you calculate the SNR? This is the input to the demodulation, right? So that's what we have here. So for xt, we are going to calculate SNR, signal power divided by noise power. That's SNR. So this is again NT, right? From now and onwards, we are not going to talk about WT. Forget WT. Okay? What you want to remember is just different. WT and NT is different, and we now we are not going to look at the WT anymore. We are going to look at NT from now and on. You always see the NT because we don't care about WT, but you want to remember the difference. So this is how to calculate the SNR, signal power divided by noise power, right? And that's the E expectation is time average. This expectation here is a time average. Therefore, time average, how do you calculate the time average? ST is typically a periodic signal. Periodic, right? So if the period is T, you know that we want to calculate it this way. That is how to calculate the expectation, right? Time average of your signal power. Also remember this is square. Square, right? It's not ST. You are integrating S square. Also noise square. Meaning this is a power. This is a power density. Signal to noise power ratio. This is not just ratio, just a power ratio, right? So that's why remember this is square. This is a simple example. Very simple example. Let's say our ST transmitted signal looks like this. Okay, just the example. And that ST is here. Our transmitted signal. That is this signal. Now look at here the second line. Assume noise is white and Gaussian with a power spectral density n naught over 2. What does that mean? That means WT, our noise in the channel, is white and Gaussian, as we said already, with a power spectral density n naught over 2. N naught over 2 is just constant value. So what that means is this level here is n naught over 2. We call this one as n naught. N 0 means nothing, right? 0, nothing. So we call it n nothing. But make it short as n naught. That's a common word. A lot of people call n naught, n nothing. Okay, n naught. So n naught over 2. That's a constant value. So that means power spectral density. This is our power spectral density over noise, flat, and this level is n naught over 2. Some value. We don't care. Okay, we don't care. Some value, but constant. So that's what they mean. Our noise looks like this. Now, in this case, we want to calculate the signal power, average signal power. And how to calculate is, as I said earlier, n naught 1 over t, because we want to take average over time. 0 to t, we want to integrate over s square dt. Okay? Once you do that, AC is a constant, AC square is constant, and also so you can bring it out, AC square right here. And cosine square will be changed to 1 plus cosine 2 times of this, right? Cosine x squared is 1 plus cosine 2x. We know the identity, right? So let me write it here. Cosine square x is same as 1 over 2, 1 plus cosine 2x. We know that, right? So we always use this. We use this identity many, many times. Okay? So that's how you change from this one to that. And then you do integration. once you do integration, this cosine 2x will be gone, right? So therefore, you're going to get this output. So that's our signal power. But remember, think about this, right? This is our signal. What is this average signal power? It's very, very straightforward. Why? Think about this way. Let's draw this ST. ST is going to be just cosine, right? So let's think about here. This is 0. This is time domain. Now this is time domain. ST will look like this. And this maximum level is AC. This is ST, our ST. ST is AC cosine. Right? Cosine something. That's our ST right here. Now what we want to do is we want to do ST square. So let's do square. Once you do the S square, S is this one, ST is this one. But we want to do ST square. This negative part will go up like this, right? Because negative square will be positive. Also, this one will be squared, so it's a little bit changed, but it's almost same. It's a little bit changed like this, a little bit, like that. So this is S square. Now what we want to do is we want to take an average, right? What's going to be the average? You know, this one, every this waveform looks same, right? So what's going to be the average? You know, average is going to be half. This is average, right? And of course, when we square, the SC will be also square. So this one is a half point. So therefore, the average is AC squared over 2. Right? So graphically, when you draw that, it's very straightforward. Okay? Always like this. So therefore, this is going to be our average signal power. Now let's look at the noise. Our noise is AWGN here, WT, but SNR is calculated here, right here, inside the demodulation, or before the demodulation, or after demodulation, right? Remember in the previous semester we calculated two different SNRs, right? Post or pre-SNR, pre-demodulation and post-demodulation. We calculate two different SNRs, right? So those are calculated here or here. You can never calculate the SNR here. So let's calculate the SNR here. You are going to consider this noise. To calculate the SNR, you never consider WT. So this word right here in the second sentence is going to tell you what the WT looks like. That looks like this. But in order to calculate the SNR, you need to always use NT because of this reason. SNR is calculated here or here. Never calculated here. Okay? Does it make sense? So we are always considering NT, not WT. Okay? So what does NT look like in frequency domain? It looks like this. Very simple. So how do you calculate the power? This is a power spectral density, meaning this level is already power. What is this level? This level is N0 over 2. N0 over 2. That's our level. Right? So this is power already because power spectral density. So how do you calculate the power? You can just calculate this area. That's just power because it's already level. Power, it's already power. Right? So this is how to calculate the power spectral density. That's this one. So N0 over 2 times 2 times BT. Why is it 2 times BT? Because this is a power spectral density and this is a BT minus BT, something like that. No. this is 2BT. Why? Because this bandpass filter is in the pass band, meaning we have a base band and pass band, right? We are talking about pass band here. So let's look at it here. This is a zero frequency. When you have a filter here, this is the area we call that as a band pass. Base band. Base band. Here is a base band. You have a carrier frequency somewhere, right? Around the carrier frequency, this is the area we call that as a pass band. We know that this is a pass band filter. Why? Why is that? This area, right? Whatever signal you are transmitting in the air, that is the pass band, right? Look at this one. This one, the frequency is a carrier frequency. So any signal with the carrier frequency, that is a pass band signal. So that pass band signal is coming into your antenna. And first thing to do is filter. So therefore, this is a pass band filter. Meaning that filter has the center. This is a filter, right? Band pass filter. The center point of this band pass filter will be always carrier frequency. That's your carrier frequency. This is what this filter look like. Okay? So that filter here is a carrier frequency. And what is this one? This is a bandwidth of your filter. That is 2BT. That is 2BT. This part is like a BT. This is the bandwidth of BT. So we have a 2. So that's 2BT. So simply speaking, band pass filter, our band pass filter, this band pass filter look like this. The middle point is FC, and this band pass, the bandwidth is 2BT. So therefore, our noise power is like this. So simply N naught BT, right? This is 2BT. The level is N naught over 2. So you multiply these two, that's going to be N naught BT. So that's our noise power. Okay, this is our noise power. So this is our signal power, average signal power. This is our average noise power. So you make it like a ratio. That's our SNR. But that SNR is measured here, right here, before the demodulation. Okay. We learned these things in the last semester. So this is just review. This picture shows you how to calculate the SNR. In order to calculate the SNR, first thing to do is you need to measure the noise power. How do you measure the noise power? Let's come back here. You want to measure the SNR here. In order to measure the SNR, first thing to do is you need to measure the noise power first. So how do you calculate noise power? Simple way to do it is you turn off the transmitter. Okay? Meaning ST is 0 because we turned off, right? If you make this ST will be 0, okay? Make ST 0, then you're going to get only noise. Okay? So XT will be only noise. So you calculate the noise power. That's this one. Okay? This is just block diagram. So no signal, meaning no transmitted signal. Then we only have a noise WT in the channel. This is channel, right? Wireless channel, something like that. So we have a noise WT. This WT is this one, right? When you have then noise, the AWGN noise coming in, here, this is a receiver, right? This is all receiver. So the first thing in the receiver is a bandpass filter. That's what we said, right? And right here is now we get NT, right? So since we have NT, now we put the power meter. Power meter is a small device to measure the average power. But what is the input? Noise. Okay? So when you put the power meter into the noise, you're going to measure only noise power, which is N. So what we get N here is the noise power. So that's how you calculate the noise power. Now once you know the noise power, later now you turn on the signal, transmit signal. Okay? You transmit something. Then of course you're going to get signal plus noise. That's how you calculate the signal power plus noise. And from those two, you can calculate the signal to noise ratio. All right. Before moving on, we want to summarize and we want to review some of the basics or some of the mathematical tools before we're moving on. So first thing to review is orthogonality. We heard this orthogonality many times, right? In communication, we see this orthogonal, orthonormal, orthogonality many different places. What is the definition of orthogonality? Orthogonality basically means that we have two different signals, and those two different signals have this kind of relationship. Then we call that as orthogonal. Okay? So what is the relationship? The relationship is V1 and V2 are different signals. It can be a signal, it can be a code, it can be any different kind of information or any kind of signal. Or it can be a vector. Okay? So vector, signal, code, all these are same in this case. Let's say you have a certain vector, V1 and V2. Right? If the V1 is doing, what is this one? What is this one? Like this, right? A, comma, B. What is this? If A and B are a vector, then this is an inner product, right? Inner product. If this is a vector. You know vector, right? What is vector? Vector is something like this, right? You have some, for example, in X component, Y component, or something like this, right? This is what we call as a vector. You have a certain component in each of the dimension. So all this is a dimension. So in this case, it's a 3-dimension, not a vector. But so that is a vector. But if you think this A and B is not a vector but signal, then what does that mean? If A and B is a signal, then this is a correlation. So inner product, if A and B is a vector, then you can call this one as an inner product. But if A and B are signals, we call this one as a correlation. It's basically the same thing. Inner product, outer product, correlation, autocorrelation, cross-correlation, all these are the same thing actually. Some very closely related. Now, what we want to do is we have two vectors, but V1 and V1, we want to take an inner product. Or V1 is a signal, then we are doing autocorrelation. Once you do that, we get some constant value, C. We don't care what the C is. Okay? It doesn't matter. But what is important is this is not 0. We have some value. But this is you are calculating a correlation with yourself. That's an autocorrelation, right? You have some signal, but you are doing correlation with your own. Then that's autocorrelation. Of course, you're going to get something, right? And what is important here is now we have two vectors. You are calculating inner product with another vector. V1 and V2, you take an inner product. And that gives you 0. Right? Or putting another way, the V1 and V2 are signals, then what does that mean? If these two are signals, then you are calculating cross-correlation. This is autocorrelation, right? Your signal is calculating yourself. correlating with yourself. That's autocorrelation. You're calculating a correlation between two different signals. That's a cross correlation. And cross correlation shows you 0. Autocorrelation gives you some value, some constant value. Cross correlation gives you 0. That is a condition of orthogonality. Right? That means orthogonal. V1, V2 are orthogonal. So graphically, what does that mean? That in order to have this condition, since this is a vector, in order to have this condition, you know that these two vectors should be like this, right? Graphically, should be orthogonal. Means that their angles between those two will be 90 degrees. Okay, graphically, that's what they mean. You can actually take an example, right? V1 in this case, let's say is 1 and 2, for example. And if this one is like -2, 1, something like that, for example, right? Then you know that this is orthogonal. Let's draw that here. This is xy Cartesian coordinate. 1, 2 will be here. -2, -2, and 1 here, right? So that's a V2. This is V1. So V1 is like that. V2 is like that. And graphically, we can see that, visually, we see that this is a 90 degree. So let's calculate the inner product. 1 and 2 vector, -2 and 1 vector. You can calculate inner product. We can see that this is 0. This is a case of vectors. But you can do the same thing for the signals, right? Let's say we have a S1 signal. We have S2 signal. We have two different signals, right? And you can actually calculate the correlation between these two. And sometimes that gives you 0. Let's take an example. What is such an example? We'll see that in the probably next slide or sometime later. But let's say S1 is simply cosine x. S2 t, this t, 2 pi fct. Just simple example. Let's say S2t is cosine 4 pi fct. Let's take a simple example like this. We say that this is orthogonal. How do you know? You can calculate the cross correlation. How do you calculate the cross correlation? Just multiply these two and just integrate, right? You multiply these two and integrate, then you can see that the output will be 0. So that means it's orthogonal. Okay. Of course, if you do square of this, right? I mean autocorrelation, then it's not going to be 0, right? Autocorrelation can never have a 0. So you calculate the autocorrelation of this or autocorrelation of this. We know that it's going to be some value. In that case, it's going to be 1/2, actually, right? We know that the power of this is 1/2. We know that, right? Same reason that I told you earlier. Cosine, you take a square and average, it's going to be 1/2. So 1/2, right? So we know that that S1t has the autocorrelation of 1/2. Same for this one. But when you multiply these two and integrate, calculating cross correlation, we know that this is a 0. So this is a very simple example for signals. This is a simple examples for vectors. But same thing basically, right? Basically same thing. So that's the concept of orthogonal. Orthogonal. And that's what that means. Okay. Sometimes we call V1 and V2 are orthonormal. And what that means is it is actually same as orthogonal. Only difference is that when you do autocorrelation, it's not going to be any value. It's going to be 1. So in order to do that, what you need to do is V1 and V2, each vector should have a size 1, amplitude 1, right? Amplitude 1, square still 1, right? So in order to satisfy this condition, this V1 and V2, all these vector or all these signal should have amplitude 1. So that's also normal. Okay, but basically same as orthogonal. Oh, yeah, so see, this is what I just said. This one is going to be dot product, meaning the inner product. If you see a vector, this is how to calculate the vector, inner product. But if the fg and fx and gx is a signal, or in this case, the real functions, you can calculate it this way by integrating those two. But sometimes the f and g, or v1 and v2, are sometimes complex functions. If those are complex functions, this is how to calculate the cross correlation. So what I'm showing you here is the original definition of cross correlation. Okay, so you need to do like f and g complex conjugate. So that's how you do in complex signals. Okay? So that is a definition of orthogonal. I guess we know all the dot product and inner product. So this is how to explain the inner product and dot product in a visual way, and also how to calculate this. So I assume that every one of you probably knows this, right? So let me skip this slide and let me move on to the next slide. There's another very common procedure called Gram-Schmidt. We learned this in another course, right? Yeah, we already learned this, I guess, in another lecture. But let's review what this means. Gram-Schmidt procedure is sometimes called as orthogonalization procedure. So what that means is we have some signals or some vectors, and what we want to do is we want to make them orthogonal. Let's say we have three vectors. Let's take an example. Always an example is easy to look at, right? So let's say we have three vectors, these three vectors. What we want to do is that we want to make these three vectors orthogonal. Okay, we want to make them orthogonal. That's what we want to do. Why do you want to make orthogonal? Why the orthogonal is important? If signals are orthogonal, right? That means what? Why is the orthogonal important? If two signals are orthogonal, that means these two are completely independent. No correlation between these two. That's what they mean as orthogonal. So we can completely separate these two, perfectly separate these two. What is always happening in communication and also in other signal processing applications is that when you have multiple signals, always this signal has some impact, or this signal has some bad correlation with another one. Always there's some correlations between signals. Correlation in general is not good, right? Because we want to separate them as much as we can. So that's why orthogonal is very important always. Okay? And this procedure here is to make these vectors or these signals to be orthogonal. So that's why this procedure is sometimes common. When you look at these three vectors, right? These three vectors does not look like orthogonal. It does not look like orthogonal, right? But we want to take this procedure in order to make them look like as orthogonal. That's the procedure. So we want to take this procedure to do orthogonalization. So first thing to do, this is how to do it, right? This is steps to do. This is like 2 pages of slides. So this is a step-by-step procedure. So first step to do is we always want to do normalization. So first thing to do is normalization. Every step you first do normalization. Okay. So we can start from the first vector. Actually, if you want, you can start from anyone. Okay, you can pick anyone. In this case, I just took the first one as the first vector, but you can start from any vector. So let's take this first vector as a starting point. The v1, u1. u1 is original vector, but just for convenience, let's call that as a v1, and we want to take the normalization. How do you take the normalization? We want to take a norm. This is a norm. Always when you have a vector or matrix, you want to take a norm. What is a norm, by the way? You have a vector or matrix. When you take a norm, you take the power of that. Okay? So you are taking the normalization like this. Once you do normalization, this vector will be changed to this vector. Then how do you know this is normalized? We call that as a W1, right? So how do you know W1 is normalized? You can calculate the W1 norm. It should be 1. So how do you calculate that? Let's do square. Yeah, square, right? Square. But this is a vector. How do you square? This is W1, right? So W1 transpose W1. This is how you calculate the square. For any vector, right? You first to typically when you take a vector, when you say vector, that is vertical vector. There's a vector like this, right? Row vector. But the general rule is that when you just call vector, that's going to be a column vector. That's a general rule. Okay, generally we call that, when you say vector, that's going to be column vector. So when you have a column vector like this, again column vector, this is how to calculate the square. This is a column vector, so when you take a transpose, this is going to be row vector. Let's call the ABC, then it's ABC. Now this is original column vector. So you calculate this is going to be square, right? A squared plus B squared plus C squared, that should be 1. That's how we call that as a normalization, right? And we know that when you do square like this way, we know that this is going to be 1, right? It's 1 over 2 plus 1 over 2 becomes 1. What about the norm of this one? That's going to be 2, right? 2. The norm of this is 2, right? So that's why we divide by that. Of course, square, right? Square is 2, so you take a 1 over 2 here, square root over 2. So that's how you get this. So first thing to do is we take this vector and take a normalization, and then we're going to get W1. So that's the first step. Now what you want to do is that this is a second step. In this second step, we calculate this one. From the original second vector, we are going to subtract the correlation between these two vectors. These two vectors. So this is correlation between the first and second vectors. Why do you subtract the correlation? Because we want to do normalization, right? Eventually, after the normalization, all the correlation should be gone. So that's why we want to remove the correlation. That's how you make them orthogonal, right? So this is a correlation part. How do you know? Because look at this one. This is what? This is a cross correlation. Correlation between U2 and W1, right? So therefore, this is a correlation part between these two vectors, and we're going to subtract that correlation. from the W2, from U2. So this is how to calculate it. Then you're going to get this. So that is our V2. But we know that this V2 is not normalized, right? So we want to take another procedure to take a normalization. So this is the W2. And that is our final answer for the second vector. So this is going to be the first vector after normalization. And this is going to be the second vector after normalization and also subtraction of correlation. So let's take a look at this one and this one. These two, right? This is W1, this is W2. When you compare these W1 and W2, we know that each one is normalized. So when you take a square, we see that the power is going to be 1. When you take a norm, it gives you 1, right? Same here. In addition, what we also know is that correlation between these two will be 0. Because we already subtracted correlation, these two are orthogonal. Right? These two are orthogonal now. So if there's only, in the original question, if we have only 2, this is the end. But now we have one more vector, right? So we have one more step to do. But W1 and W2 are final answer for the two vectors, first two vectors. But now we have one more vector, so let's keep moving. And the last step to do is the same thing repeated in the same way. U3 is our third vector. And what we need to do is, from the third vector, we are going to subtract correlation between the third vector and the first vector. Also, we are going to subtract the correlation between the third vector and second vector. Right? We have 3 vectors now, right? So the third vector will have a correlation between the first one and also correlation to the second one. So we're going to subtract those 2 correlations. Same way as we did before. Once you do this, you are going to calculate it this way. Now we get this answer. And after that, what we want to do is we are taking normalization. But this is already normalized. So it does not change anything. So that is a W3. So this is how we calculate the final vector. So this is the answer. W1, W2, W3. That is our final answer for this procedure. So once you look at these 3 procedures, these 3 vectors, now what we know is that this is normalized, this is also normalized, this is also normalized. We have a 3 normalized vector, right? And we see that correlation between these 2 is 0. Correlation between these 2, again 0. This one, again 0, right? So all the vectors have no correlation with each other. That means orthogonal. And actually, in this case, it's orthonormal, right? Because it's normalized. That's the procedure. That's the end. We're going to have this one in the homework, okay, today. In the last slide, you see the homework, right? Homework is already uploaded, so you can practice this one in the homework. This last one here is how to recover the original vector from this. Okay, so let me explain the last one here. This is basically what it means. Basically, this is how to calculate the procedure. Okay, like pretty much easy to do, but let me visualize what this means. Right? It's always easy to remember when you look at it visually. Right? So let me explain to you one more time. The same thing in a visual way. So this is our XYZ coordinate. Our original vector is u1 is 1, 0, 1. So this is x, y, z. It's like 1, 0, 1. So it's 1, y is 0, z is 1. So it's right here. That's u1. I'm basically drawing the original vectors, right? And originally u2 was 1, 0, 0. So this one was u2. In the original third vector, 2, 1, 0. So it's like 2, 1, 0. So it was here. That was our original u3, right? So these three vectors was original vector. Okay, actually let me make it a little bit bigger. Let me reiterate here. 1, 2, 1, 2, 1. So here is u1. This is u2. This is our original vector, u1, u2, u3, right? And when you look at these things, right, these are not orthogonal. Our original vector u1, u2, u3 are not orthogonal. Why is that? Because look at here, u1 and u2, between these two we have only 45-degree angle, right? It's not 90 degree. Between these two also, right? It's like 2, 1, it's like maybe 30 degree. So we know that these three vectors, original vectors, are not orthogonal. So therefore, using this Gram-Schmidt procedure, we are going to make them orthogonal. So let's take a look at it visually, what this basically means. Eventually, when you do these procedures, we're going to get this, right? But let me take a u1 and u2. Let me take a u1 and u2 first. Okay, this is u1, u2. I'm basically taking these two only, right? Make it bigger. And then let's take a look at it here. First thing to do is, what was the first step in the the Gram-Schmidt procedure? First thing to do was normalization, right? Actually, even before that, first thing to do is you need to take which one is the first vector you start. And we just simply started from u1. So this is my first vector to start with. Okay, and the next step to do is we need to take a normalization. So let's take a normalization of u1. This length actually is root square 2. So you take a square, then it's going to be 2, right? And we want to take a normalization, then it's going to be like this. So this vector right here is going to be our w1. Okay, the previous w1, right? This one. This is our first answer. Just simply normalization. Because first vector, you don't have to do anything. Just normalize it. That's it for the first vector, right? So this is our w1. And we know that this point is this one, right? Root square 1 over root square 2, 0, 1 over root square 2. That's going to be our first answer, w1. Okay, that's what we did here as a step 1. Now we want to take a step 2, this one, right? We want to take this step. And what is this step? What this basically means? This step basically means is one vector minus another vector. The second vector is going to be correlation, but it's going to be vector. So it's like what? So it's going to be like one vector minus another vector. Simply a vector subtraction, right? Simply speaking. So u2 in this diagram is this. Okay? And what is this one? This is a correlation, right? you know the inner product like this is related to the projection. You heard about projection before? So simply speaking, this part, this red part, is the projection of U2 onto W1. It's basically the same as that. What does that mean? What is a projection? Projection is like this. Let's say we have two vectors, A and B. We are going to project A into B. Okay, we are going to project from A to B. That means you are going to project like this. Think about that we have a light here. Right? And you're going to do a projection. Then we know that we have a shade here. Shade, right? So that's a projection simply. So this part, the projection, how do you get this projection? We have a cosine between these two. We know that this is A. This part right here is A cosine theta. Right? This is A cosine theta. That's a projection. When you look at here, right? What is the inner product? Inner product is U2 amplitude times W1 amplitude times cosine theta between these two. So it's like a U2 amplitude times W1 amplitude times cosine theta between these two. But you're going to multiply W1 again, right? Actually, we have to do normalization here. U1 like that, and you multiply W1. So eventually when you multiply these, then what that means is it's going to be like this, A cosine theta. So it's going to be projection. So this one, that red circle is going to be a projection of U2 onto W1. So U2, you're going to make, in this case I make it a little bit bigger. Actually this one, U2 actually has the amplitude 1, so let me make it more accurate. So that's going to be U2. I think I make it too big here. Because this is now normalization, so size is 1. This one, U2, also needs to be 1. Okay? You're going to make a projection like that. Make a projection into W1. So that is this part. And you're going to remove that part, meaning that W2, which is this, right? Minus this projection. That projection, this red part, is actually this one. Okay, let me do it again. When you take a projection of A into B, this is the projection vector. This is a projection. That is a projection. So when you take a U2, project into W1, the output, projected output is going to be this. That's our output, projected output. That's this one. This part right here is a projection, meaning this vector. In this case, it just so happened that W1 and this one actually looks the same size. But in general, this one is a projection vector from A to B, right? This is the projection vector. In this case, it looks almost the same, but just happened like that. But this one is a projected vector of this one. Now what we want to do is U2 minus this. So this one minus this, right? In that case, minus this. So this is going to be like that. In that case, what's going to be our V2? Our V2, probably this vector. This is our V2. Because U2 minus this vector. This is U2 vector. This is a projection vector. So this V2 vector minus this vector will be this. So that is our V2. This. Okay? Visually, that is our V2. Now, after we get V2, what we need to do is we take a normalization of V2. So this is now should be normalized. So it's going to be like this. So that is our W2. After normalization, we're going to get W2. Once I do that now, eventually what we learned from these two is that we got W1 and W2, and this is going to be W1. This is going to be our W2. These two are now orthogonal, right? Because we subtracted projection, now this is eventually W1, this is eventually our W2, so we get W1 and W2 are orthogonal. So this is how to move, right? Now let's move on to the last one. This is a V3. V3 is right here. And how to do that is from the V2, V3, we are taking projection, another projection, like that, right? So we are taking this one projected into W1, this W1. W1 is somewhere here. So we are taking projection like that. And also U2, W2 is somewhere here. This is W2. I'm just moving this one into here, right? This is W2. And this one, I'm going to project it here. And we're going to subtract that. Then we're going to get this. So after you do all this, the conclusion is this one, but let me tell you what this basically means. We are getting W1 and W2, W3 like this. So let's draw these three vectors into this coordinate. W1 is somewhere here. Here. This is W1. W1 is on the same line as U1, right? W1 is simply just normalization of U1. So W1 is somewhere here. Now W2 is Z is minus 1 over 2. So Z1 is somewhere here. This is W2. This is W2 somewhere here. So x-axis is 1 over root square 2, but y is 0, and z component is minus 1 over root square 2. So still in the x and z plane, but W2 is somewhere here. So it's going to be, of course, orthogonal. Now this W3 is, eventually all this calculation gives you this is W3. Okay? This W3 is x is 0 and z is 0, y is 1. So it's going to be somewhere here. Okay, that's the answer. But what does that mean, basically? Here's one thing very important. What is basis? I call that as an orthonormal basis. But what does that mean? This is what that means. Okay? When you look at the original U1, U2, U3, these are not orthogonal. Not orthogonal, right? But we are basically changing this U1, U2, U3 in a different way, but this concept is like this. We think that U1, U2, original U1, U2, U3 are not orthogonal because that we have x plane here, y plane here, z axis here. But what we can do is that we can rotate this space. X here, y here, z here, right? But we can rotate this whole x, y, z plane space. And also we can change the origin, or we can rotate the space. When you rotate the space, right, and then you can move this around, then you can make them orthogonal. its concept is something like that. Something like that. But simply speaking, as I said here, you can see now the visualize that this W1 and W2, W3 are now orthogonal. But think this way. W1 and W2, W3 are orthogonal. So now this is a new axis. Original X is here, original Y is here, original Z is here. But now everything is changed. Everything is changed. After this whole procedure, everything is changed. Now this is X. This is Y. This is Z. Something like that. Think about that way. That's why we call this one as a basis. What is a basis? Basis means that it's a basic vector that decide the whole space. That's a basis. Original X, Y, Z, you know this three-dimensional Cartesian coordinate, right? What is the basis of this X, Y, Z? The basis of X, Y, Z that we know is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is like a basis we know. That is a 1 here, X, Z, Y, right? That's the basis we know in the previously, right? But now I'm changing these things and I'm making a new basis. Why do you need a new basis? Because we want to make them orthogonal. So if you use these bases, now we have a new X and new Y and new Z, right? You're basically changing new space, new coordinate. Once you use this X, Y, Z, this U1, U2, U3 are now orthogonal. That's what that means. That's why you see this is a basis, new basis. And using this new basis, where is the U1? Now think about that. Now we have a new X, a new Y, new Z, right? Okay, we have a new basis now. So based on the new basis, where is the U1? U1 is here, meaning W2, 0, 0. Based on the new axis, new coordinate system. Where is the U2? U2 is 1 over W2, 1 over W2, 0. That's the position of U2 in the new XYZ system. Okay? U3 also W2, W2, 1. That is the position of this U3 vector in the new XYZ basis system. That's what this means, the last one. Okay. Okay, the last one is the QR factorization. This is another very common procedure that we always use. What this basically means is that we have a vector. Originally we start from 3 vectors, right? We have 3 vectors and put them together and we want to make a matrix. Okay? In this case, 3 by 3 matrix. And using this 3 by 3 matrix as an input, this matrix is going to be your input. And put this input into QR factorization procedure. And the details of how to calculate the QR factorization, we are not going to talk about that. And what we're going to talk about now is that why do we use QR factorization? How to use the QR factorization? Okay, inside the QR factorization, how you calculate all these things, you don't have to worry about here. You can run MATLAB. Okay, run MATLAB. In MATLAB, you have a QR command. Just run MATLAB. You're going to get output, right? So we don't care about how to calculate it. What we want to know is that that's going to be input 3 by 3 matrix. Put that into the QR factorization using MATLAB. You're going to get the output. Output is going to be 2 matrix. The first one is a Q matrix. Second is an R matrix. And the why we are using QR factorization is because we want to make this kind of matrix. What is special about this matrix? This is an upper triangle matrix, meaning that this is upper part, you have a non-zero. Lower part, you always have a 0. That's called the upper triangular matrix. Sometimes using QR, you can sometimes get a lower triangular matrix, meaning that lower part you have a non-zero, upper part you have a 0. That's a lower triangular. In this case, it's upper triangular. And Q is another vector, but this Q, this is a matrix, right? But we have 3 vectors. What is these 3 vectors? I'm basically using the same example, right? This is our previous same example. U1, U2, U3, same previous example, right? So what is this Q? These 3 vectors. That 3 vectors is same as, let's go back to previous one, same as our orthonormal basis, right? Look at these 3. These 3 orthonormal bases and the Q function, Q matrix, same. Okay? These are orthonormal bases. What about R? You know the R is, in this case, upper triangular, right? And in the R, let's look at also the 3 columns. What is each column in this case? Let's go back to previous slide. I told you, right, with the new basis, when you look at this original U1, U2, U3, based on the new X, Y, Z axis, you're going to know that this is the position of U1 in the new axis. This is the position of the U2. This is the position of U3, right? So R tells you that one. R tells you the position of your original vector in the new system, in the new coordinate system, right? So this is actually same procedure of orthogonalization, but you can run the MATLAB, right? So you get the answer right away. So that's the idea here. Okay. Let's continue next one.